Good morning, everybody. I am Indrajit Bandopadhyay. So, today our topic of discussion is linear programming problem. Today, our topic of discussion is linear programming problem. Linear programming problem. So it is a typical process of optimization. Actually, we have three types of optimization. One is optimization with no constraint. We call it unconstrained optimization. So the first type of optimization is unconstrained optimization. That means we want to maximize or minimize one objective function, but we don't have to face any kind of bottlenecks, any kind of constraints in practice. So if we get that kind of situation, mathematically we handle it through the normal course of maxima and minima. That means we have to find out the first order condition, dy dx equal to 0, and the confirmatory test for that the second order condition. If d2y dx square is negative, then the objective function, that means the value, shows the maximum value, and if d2y dx square is positive, then normally we get the minimum value. So this is how we can solve it. Sometimes we get the optimization problem of an objective function with a single constraint. For example, sometimes we would like to maximize our utility satisfaction, but we have the affordability as constraint. That means we have our budget constraint. So the problem is maximization of utility subject to budget constraint. So in that case, this is the optimization of the objective function, but we have to face only one bottleneck, one constraint, that is the budget constraint. So how to deal with that mathematically? Here, normally we construct a Lagrangian composite function. We find out the partial derivatives. The first order partial derivatives should be 0, and in order to get the confirmatory test, we have to construct a bordered Hessian determinant. If the value of the bordered Hessian determinant is positive, then the function is maximized. If the value of the bordered Hessian determinant is negative, then the value is minimized. So this is how we can solve it. Sometimes through Kuhn-Tucker condition also, we may find out the solution of this optimization problem. Now, when we can apply the linear programming? In which situation? First we have to understand that if there is one objective function with multiple constraints, in practice it is very much prevalent that there is only one objective function but lot many constraints are there. Like in a production process, labor may be a constraint, other resources may be a constraint, capital may be a constraint, supplier may be another constraint. So many types of constraints a manager has to face in order to maximize the revenue, maximize the profit, maximize the market share, minimize the cost, maximize the output, minimize the loss, etc. So here also you see that we want to optimize one objective function, but subject to multiple constraints. So when the situation is like this, then we may apply linear programming. We can take linear programming as one of the solution processes. Now, what is the limitation of the linear programming? Because before going to the solution process, we have to understand that in which situation we should apply and in which situation we should not apply. So what is the limitation of the linear programming when we cannot apply it? Number one, if there are multiple objectives or multiple goals, if there are multiple objectives or multiple goals with multiple constraints, then linear programming may not be a fitting solution process. In that case, we have to apply goal programming technique. This is another operation, the technique of operations research, what technique. So there we have to apply goal programming. Suppose we need only the integer value. Sometimes, suppose you are running a goattery or a dairy. So you need to understand that how many cows, how many buffaloes, how many goats you have to keep in order to maximize the milk production. You apply linear programming and you will come up with the solution that you have to keep 13.67 number of cows, 2.38 number of buffaloes and 30.27 numbers of goats. So the solution is meaningless because cows, buffaloes and goats cannot be maintained in fraction. So that means here we need only the integer value as our solution. We can't accept the fractions as our solutions. If it is a maximization of manufacturing of any chemicals, then how much sulfuric acid can be used, how much nitric acid can be used. In that case, we can accept the answer as fraction. That okay, fine. If I use 37.37 liters of sulfuric acid, then this chemical production will be highest, will be maximum. So there is no problem in it. But in case of my previous example, there is a problem because we need only the integer value and we can't accept the fraction. So in this case also linear programming is not the right tool to apply in order to find out the decision making. So there is another mathematical process named integer programming, so that we have to adopt for getting the solution. Now you know that the environment is dynamic. So linear programming is a static model. So if we want to incorporate the flavor of the dynamism into it, then linear programming has its own limitation. We should go for dynamic programming. So out of the limitations of the linear programming, the three programming techniques have been emerged, named goal programming, integer programming and dynamic programming. So through those means applying those programs, we can come out of the limitation of linear programming. Now linear programming means what is the nature of the problem. So first let us discuss about it. Suppose a carpenter knows that he has to produce some chairs and tables in order to maximize his profit. If he can sell one chair, he will get 12 rupees profit. If he can sell one table, he will get 5 rupees profit. There are some ingredients, some raw materials, some labor hours which are required to produce chairs and tables. And those resources are not plenty. It is not, abundantly available. So those are scarce. So maintaining those scarcity, keeping those constraints in our mind, that carpenter has to decide how many chairs and how many tables he should produce in order to maximize the profit. So let us take some values here. Suppose the number of chairs the carpenter should produce is x1. The number of tables the carpenter should produce is x2. Now what the carpenter knows? The carpenter knows that if he can sell one chair, then his profit is rupees 12. And if he can produce and sell one table, then he will get 5 rupees per table from the market. So that means here the objective function is profit. If the profit is indicated by Z, say profit, so he has to maximize Z. His objective is to maximize Z, and since he is producing and selling x1 number of chairs, so from the chairs he will get 12x1, that is the profit, because per chair he is getting 12 rupees, and since he is producing x2 number of tables, so then he will get 5x2 profit by producing and selling tables. So the total profit comes as 12x1 plus 5x2. Here profit is denoted by Z, and that carpenter has to maximize the profit, that Z. Now there are some limitations. Say for making chairs, 2 types of timbers are required. For making chairs, 2 types of woods, timbers, 2 qualities are required. So for making chair, 2 units of timber 1, first type of timber, is required for making 1 chair, and for making tables, 3 units of first type of timber is required. So 2 units of first type of timber is required for making chair, 3 units of first type of timber is required for making table 2. And how much timber is available with the carpenter? For example, say 30 units of timber. So that 30 units is the limitation to that carpenter. He could not use more than 30. So either he has to use equal to 30, or it is better if he can manage the entire show by using less than 30 units of first timber also. So this is the constraints for raw material 1. Raw material 1. Now timber 2 is also required. Second quality of timber. So for example, 5 units of the second quality of timber is required for making 1 chair, and 1 unit of second type of timber is required for making table, and only 20 units of second type of timber is available with this carpenter. So he cannot use more than 20. Either he can use 20 units equal to 20, or it is better for him if he can utilize less than 20 then he can save some of the cost from timber 2. So this is the constraints of second raw material. Second raw material related constraint. So raw material 2. Now for making tables and chairs, labor hours are required. So suppose for making one chair 10 labor hour is required, and for making one table 7 labor hour is required. Total available labor hour is 50 hours. So more than 50 labor hours cannot be available to that carpenter. So similarly, this is less than equal to 50. This is the constraint related to labor hour. So maintaining these three constraints, the carpenter has to maximize the profit. And chair and table cannot be produced in negative. We may drop producing any one, either chair or table, in order to maximize the profit. That means the value of the chair or table extremely may be 0, but it cannot be negative. -1 unit of production of chair is not possible rationally. So that's why the value of x1 and x2 should be greater than or equal to 0. This is called a non-negativity constraint, because chairs and tables cannot be produced in any negative unit. So this is how a linear programming problem can be formulated. This is the formulation of the linear programming problem. This is how it can be formulated. Now after formulation, we have to think that how to solve it. What is the solution process? So the solution process are twofold. That means in two ways we can solve. The first process is called the graphical process. And the second process is called simplex. SIMPLEX, simplex. So these are two processes through which you can solve this kind of linear programming. Graphical solution has its own limitation. If we have only two variables, like in this example, there are only two things, chairs and tables. We don't want to produce any almirah. So there are only two variables, x1 and x2. So since we are comfortable with a graphical representation with two axes, two-dimensional graph, so that's why if the number of variables are more than 2, then graphical solution cannot be recommended. It is not a right process to find out the solution. Then we have to go for the simplex method to solve the linear programming. So here only two products are being produced, chairs and tables. That's why this problem contains only two variables, x1 and x2. So this problem can be solved through graphical process. But if we add another products, say almirah or divan or dressing table or anything else, more than two variables, then here we will find out x1, x2, x3, x4, etc. more than two variables. Then the graphical solution is impossible. Then we have to go for the solution through simplex method. So this is the solution process of a linear programming problem. Now if we want to solve it through graph, then how it can be solved, that also first we have to learn, and then we have to learn that how it can be solved through simplex. So simplex is based on certain heuristics, certain tables we have to prepare for solving this problem through simplex. Simplex is an improvement over the graphical. That means if you get any problem, you can solve it through simplex, and if the problem is a problem of two variables, then you can solve it through graphical process also. So that's why simplex is an improvement over the graphical solution. So now we have to discuss that how this problem can be solved through graphical process first, and then we have to see how this problem can be solved through the process of simplex. So before starting the graphical process, just one and two things we have to remember. We should learn the we should know about the basics of the concept of straight line. Straight line, in a straight line, if we talk about the ideal equation of a straight line can be represented by y equal to mx plus c. This is called the ideal equation of a straight line, where m is the gradient and c is y-intercept. Suppose this is a straight line, y-axis, x-axis, then this straight line is creating an angle with the x-axis. Say this angle is 45 degree for our example, and this straight line intersects the y-axis, creating a positive segment of 3 units. 1, 2, 3. So then the value of m for this straight line is the tangent of the inclination, tan 45 degree, the value is 1, and the value of c in this case is 3, because for this straight line the y-intercept is 3 units. So what would be the equation of the straight line AB? Equation will be y equal to mx. The value of m is 1 into x plus c plus 3. Therefore y equal to x plus 3. So this is the ideal form of a straight line. Now apart from the ideal form, a straight line can be represented in the different way also. One of the popular form is the intercept form. So let us see what is it. Because for doing the graphical solution, the intercept form would be important for us. Once we understand what is the intercept form, then we can understand that how we can apply the graphical solution to find out the answer of this linear programming. So that's why we should know what is the intercept form of straight line. So let us see that. Suppose this is a straight line. Which cuts the axis, y-axis and x-axis. This straight line cuts the x-axis with a distance a unit from the origin and cuts y-axis with a distance b units from the origin. That means here the coordinate is a0 and here the coordinate is 0b. So for this kind of straight line, we use the intercept form to find out the equation of the straight line x by a plus y by b equal to 1. Suppose in this case, the value of a is 4 and the value of b is 1, 2, 3, 4, 5. The value of b is 5. So then the equation of this straight line will be x by a. So value of a is 4. So x by 4 plus y by b. So the value of b is 5. So y by 5 equal to 1. If you make an LCM, then it is 20, 5x plus 4y equal to 1. So that means the equation of the straight line is 5x plus 4y equal to 20. This is called the intercept form of a straight line. So this intercept form will be applicable in order to find out the graphical solution of this linear programming problem. So in my next lecture, I will show you that how this problem can be solved through graphical solution. Thank you.